So, imagine a blindfolded jeweler,
Okay.
and they're tasked with cutting this priceless, like incredibly fragile diamond. But to keep the gem secure, it's been locked inside a thick, opaque titanium box.
Right, so they can't see it at all.
Exactly. The jeweler has to use these remote-controlled mechanical arms to reach inside and cut the gem. They can, feel their way through the delicate movements, and they execute the work perfectly, but they never actually see the jewel itself. They just hand the lockbox back to the owner when they're finished.
That is a really vivid way to look at it.
Yeah, and welcome to today's deep dive. Our mission today is to explore a concept that cryptographers consider like the holy grail of their field. It's called homomorphic encryption.
The big one.
The really big one. And we're pulling from a comprehensive set of source materials today, mostly this really extensive Wikipedia overview on the subject, just to understand how we can process and analyze data while it remains entirely encrypted.
Which is huge for, safely outsourcing our digital lives to the cloud.
Right. Because right now, you have to trust the cloud provider. But if this works, maybe you don't. And I want to make sure you, the listener, have a really clear, jargon-free shortcut to understanding this tech, because it's probably going to be protecting your personal data very soon. So, okay, let's unpack this. How close is that blindfolded jeweler analogy to the actual mechanics of homomorphic encryption?
The analogy actually holds up incredibly well to the underlying mechanics. The jeweler essentially represents a computer server in the cloud, right?
Okay.
And the mechanical arms, those are the mathematical operations being performed. And the diamond is your sensitive data. But the critical part of your analogy is that the jeweler never sees the diamond.
Because the box is locked.
Exactly. In conventional computing, if you want a server to, say, search a database or organize files or run analytics, you have to give that server the decryption key.
Right. The data has to be translated from encrypted gibberish back into plain text before the computer can even do anything with it.
Yeah, and the moment it's in plain text, it's completely exposed. That creates a massive opening for what we call a privilege escalation attack.
Which means if a hacker gets in while the data is being processed,
they can just walk away with the plain text.
Yeah.
But homomorphic encryption, or HE, aims to close that window of vulnerability permanently. The server performs computations directly on the ciphertext, which is the encrypted gibberish.
So the output of the computation is just more encrypted gibberish.
Exactly. It's only when you download that result back to your own device and apply your private key that the gibberish suddenly resolves into the correct unencrypted answer.
That's wild. And the source material gives a couple of really practical examples of this in action, which I think highlights why you should care about this. Think about predictive analytics in healthcare.
Right? That's a perfect example.
Yeah, a hospital has mountains of patient data that could be used to train AI models to predict disease outbreaks or patient outcomes. But because of privacy laws, they obviously can't just hand patient records over to a third-party tech company.
Right, HiPK and all that.
Exactly. But with homomorphic encryption, the hospital could basically lock the records in that opaque box, send the boxes to the cloud, and the cloud runs its machine learning models without ever seeing the files. Then it just sends back an encrypted prediction. The cloud provider learns absolutely nothing about the patients.
You see similar applications in image processing, too. Like, you could send an encrypted photograph to a lookup service to scan it for points of interest.
Like trying to identify a landmark or something?
Yeah, exactly. The service runs its algorithms over the encrypted data, finds the landmark, and sends you the answer, all without ever actually viewing your photo.
Though I will say, the sources provide a very necessary warning right up front about side channels.
Ah, yes. The metadata issue.
Right. Because the math itself might be perfectly secure, meaning the box cannot be broken into. But observing the behavior of the system still leaks metadata. Like, an observer might not see the photo of the landmark, but they can see that your device sent a massive packet of data to a lookup service at, 3 in the afternoon.
It's a really vital caveat. Cryptography secures the contents, but traffic analysis reveals context. The metadata is still visible. But to understand how the locked box computation actually works without decrypting the contents, we really have to look at the different flavors of homomorphic encryption.
I know, Jeevers.
Right, yeah. They're categorized by the type and complexity of the mathematical operations, the circuits that they can handle.
Right, and they range from basic arithmetic to incredibly complex operations. Like first, there's partially homomorphic encryption, which means the system supports only one type of mathematical gate.
Just one.
Right, so you can do addition or you can do multiplication, but you definitely cannot do both. The source notes that the famous RSA crypto system is actually partially homomorphic. It allows you to do an unbounded number of multiplications on encrypted data.
And then there's the Paillier crypto system, which allows for unbounded additions. But building on that, if you want more flexibility, you move up to somewhat homomorphic encryption. This one allows for two types of gates, both addition and multiplication, but only for a limited subset of circuits.
Meaning it has a ceiling on how much math you can do, right?
Exactly, it hits a limit. From there, we reach leveled, fully homomorphic encryption, which supports arbitrary circuits with multiple types of gates, but only up to a predetermined bounded depth.
Okay.
And finally, the ultimate goal, fully homomorphic encryption, or FHE. This allows for the evaluation of arbitrary circuits of unbounded depth, meaning you can run literally any computer program of any length or complexity on the encrypted data.
Okay, I want to push back on that bounded depth concept for a second, because this is where the physical reality of the math seems to get really weird.
It does get weird.
Yeah. The sources focus heavily on this idea of a multiplicative ceiling. Let's say partially homomorphic encryption is a calculator with only an addition button, and somewhat homomorphic encryption gives you a calculator with a multiplication button, but the battery magically dies after 5 uses.
That's a fun way to picture it.
Thanks. But why does doing too much math break the encryption? Like, what is actually happening inside the lockbox that causes it to fail?
Well, what's fascinating here is that to make homomorphic encryption function at all, the ciphertext must be inherently malleable.
Malleable how?
The server has to be able to manipulate the encrypted gibberish in a way that fundamentally changes the hidden plaintext inside. But to prevent attackers from just easily reverse engineering that malleability, cryptographers have to inject a small amount of mathematical noise, or like intentional error, into the encryption.
So the noise is like static on a radio transmission.
That is a highly useful way to visualize it. Yes, every time the server performs an addition on the encrypted data, that static grows just a tiny bit.
Okay.
But every time the server performs a multiplication, the static compounds exponentially. It multiplies the noise. So if the mathematical circuit is too deep, meaning you perform too many multiplications, the static eventually overpowers the signal.
Oh, man. So when you finally download the result and use your key to open the box,
the original data is completely drowned out, the decryption fails, and the data is lost forever.
that is just a wild concept. The very feature that keeps the data secure, the noise, becomes the exact thing that destroys the data if you manipulate it too much.
It's a huge paradox.
Yeah.
And the problem of how to stop that noise from destroying the data went unsolved for decades. I mean, the source notes the concept of homomorphic encryption was first proposed back in 1978, barely a year after RSA was published.
Right. And for over 30 years, the cryptography community didn't even know if a solution was mathematically possible, right?
Yeah, they had no idea. Researchers built systems that allowed unlimited additions, but maybe only a single multiplication. But the holy grail of fully homomorphic encryption remained purely theoretical. It was this massive bottleneck in computer science.
Well, until 2009, when a researcher named Craig Gentry figured it out using lattice-based cryptography, creating the first plausible fully homomorphic encryption scheme.
Yes, Gentry's breakthrough.
And his workaround for the noise problem was a mechanism he called bootstrapping.
Bootstrapping is honestly one of the most elegant concepts in modern cryptography. Gentry realized that it was impossible to stop the noise from growing during multiplication. The static was essentially a law of physics for this kind of math.
So he couldn't stop it.
Right. So if he couldn't stop it, he had to find a way to clean it up mid-computation before it destroyed the signal.
Here's where it gets really interesting. Let me see if I have this right. It's like having a photocopy of a document. Every time you copy the photocopy, it degrades and gets grainier, right?
Exactly. That grain is the noise.
So bootstrapping sounds like having a machine that perfectly redraws the faded text onto a fresh sheet of paper. But the machine itself is entirely blind and never actually reads the words. It just resets the noise back to zero, give you a fresh, clean ciphertext.
That captures the outcome perfectly. But to explain the mechanics of how the blind machine does that, we have to look at recursive self-embedding.
Recursive self-embedding, that sounds intense.
It is a bit. Gentry designed a scheme that was capable of homomorphically evaluating its own decryption circuit.
Wait, evaluating its own decryption circuit, how does that even work?
Okay, let's go back to your locked box. You have a titanium box, and the static inside is getting dangerously loud. Before it ruins the diamond, the server wraps your box inside a second, slightly larger titanium box.
Okay, so now you have a box inside a box.
Right. Then you, the user, provide the server with an encrypted version of your key. The server uses its mechanical arms to take that encrypted key, reach inside the outer box, and unlock the inner box.
Oh, so the inner box is open, but the diamond is still safely locked inside the outer box.
Precisely. The data is never exposed to the open air, but because the inner box was unlocked, the accumulated noise from the previous computations is stripped away.
That is brilliant.
It really is. You're left with a brand new, fresh ciphertext with baseline noise holding the exact same value. And because of this, you can string together an infinite number of additions and multiplications. You just pause and bootstrap whenever the noise gets too high. Gentry proved that any scheme capable of this self-evaluation could be converted into a fully homomorphic scheme.
Okay, but there is a massive catch in the source material, like a really big one.
The processing time.
Yes. The original implementation by Gentry and Halevi took about 30 minutes just to process a single basic bit operation. And a bit is literally just a 1 or a 0.
It was very slow.
If it takes half an hour to do one microscopic calculation, aren't we talking about years just to load a basic web page or process a simple text document? How could anyone consider this practical?
Well, you have to view that 30-minute metric through the lens of scientific progress. At that moment in 2009, speed was completely irrelevant. It was entirely a proof of concept.
Oh, so just proving it could be done at all.
Exactly. The value was in proving that the underlying cryptographic assumptions like problems over ideal lattices could be used to achieve the impossible. Gentry broke a 30-year stalemate. And once the community knew it was possible, other pathways opened up almost immediately.
Like that.
Well, by 2010, Van Dyke and a team of researchers presented an alternative scheme using simple integers instead of complex ideal lattices. The floodgates were open.
Okay, so the academic world knew the lockbox worked. The blindfolded jeweler could reset their tools without destroying the diamond. But to make this viable for commercial cloud computing, where servers crunch petabytes of data, they needed to speed it up by several orders of magnitude. Which brings us to the race for efficiency, generations 2 and 3.
Yeah, the subsequent generations of FHE schemes focused entirely on optimization. In the years following Gentry's breakthrough, roughly 2011 to 2012, researchers developed schemes like BGV and BFE.
And what did those do?
They drastically slowed the growth of the noise during computations. The static simply didn't build up as fast, meaning you didn't have to perform that slow bootstrapping process nearly as often.
Though the source did mention some missteps, right? Like NTRU-based schemes, I think they were called LTV and BLLN.
Yes. Those failed because they relied on an overstretched variant that ended up being vulnerable to subfield lattice attacks. It was a dead end. But the successful Gen 2 schemes thrived.
The source mentions they also achieved nearly optimal asymptotic complexity using a technique involving SIMD single instruction, multiple data. They were packing multiple plaintext values into a single ciphertext to compute on all of them simultaneously.
Yes, SIMD packing was a game changer.
I want to try an analogy for this. If we're packing multiple plaintext into one ciphertext, is it like stuffing hundreds of passengers onto a massive train, so you only have to make one trip instead of driving them all individually in cars?
That's actually a great way to put it.
But wait, it definitely saves time, but does that limit the route the train can take? Like, do we lose computational flexibility just to gain speed?
If we connect this to the bigger picture, you do face routing constraints with SIMD packing. To use your train analogy, you cannot tell passenger A to get off in New York and passenger B to get off in Chicago. The entire train goes to one destination.
Right.
In computational terms, operations must be applied uniformly across all the packed data slots at the exact same time. You apply the exact same mathematical instruction to the entire vector of data.
Which sounds pretty limiting, to be honest.
It does, until you look at how cloud analytics actually work. Think about it. If you're searching a massive encrypted database or performing statistical analysis on healthcare records, you usually want to apply the exact same comparative operation to millions of data points anyway.
Oh, I see. So the constraint doesn't really matter for those use cases.
Exactly. The vector constraint doesn't hinder the goal, and the speed gain is astronomical. In fact, these optimizations made many applications so efficient they could run in what's called leveled FHE mode.
Leveled FHE, that's the one where you know the depth of the circuit ahead of time, right?
Correct. If a software engineer knows exactly how many multiplications a specific program requires and the noise grows slowly enough, the program might never even hit the noise ceiling.
So no bootstrapping at all?
None. The server can run the entire operation from start to finish without ever needing to pause for the slow, expensive bootstrapping process.
That's a huge leap in practicality. But the cryptography community didn't stop there. The source highlights a massive paradigm shift around 2013 and 2014, the third generation. Researchers proposed new techniques, I think GSW has mentioned, that avoided expensive relinearization steps.
Yes, and that led to schemes like FHUW and TFHE, where they made a really bold choice. They decided to refresh the ciphertext after every single operation.
Which seems completely counterintuitive at first glance. Like, if bootstrapping is the slowest part of the entire process, why would doing it more often make the system faster? That sounds like a terrible idea.
Right, it seems backward. But the breakthrough was in how they simplified the logic. By restricting the computations to very basic Boolean gates, the bootstrapping procedure itself became incredibly lightweight.
So it wasn't this massive, heavy process anymore.
Exactly. They weren't running a massive, heavy decryption circuit. They were running a highly optimized, tiny one. So by 2016, these schemes dropped the bootstrapping time from Gentry's original 30 minutes down to a fraction of a second. We're talking less than 0.1 seconds per operation.
Wow. From taking a coffee break to the blink of an eye.
Yeah.
So the community conquered basic, exact computations, making them lightning fast. But the tech landscape in 2016 was undergoing a seismic shift, wasn't it?
It absolutely was.
Yeah, the biggest demand for cloud computing was no longer running exact database searches. It was machine learning. It was AI. And machine learning doesn't really rely on perfect, exact integer math. It relies on messy, continuous, approximate math.
That's the challenge. Machine learning models utilize weights and biases that are often tiny decimal fractions. The FHE schemes we've discussed so far were they handled integers perfectly.
Well, not fractions.
Right. If you try to multiply complex fractions in those older schemes, the scale of the numbers blows up, and you have to use heavy bootstrapping just to manage the sheer size of the data. To make privacy-preserving machine learning work, the industry needed an entirely different approach.
And the source points to a specific scheme introduced in 2016 called CKKS. This scheme supports fixed-point arithmetic, which is commonly referred to as block floating-point arithmetic, meaning it's designed specifically to handle those complex decimals.
Crucially, CKKS includes an efficient rescaling operation. Instead of the scale of the numbers blowing up after a multiplication, CKKS allows the server to simply scale down the encrypted message.
Well, that makes sense.
Yeah, this makes evaluating the polynomial approximations used in machine learning incredibly fast and efficient. It basically became the gold standard for running AI models on encrypted data.
But, and this is a massive but in the source material, CKKS is an approximate homomorphic encryption scheme. It introduces non-deterministic and deterministic approximation errors. It's like slightly floppy by design.
Yes, it trades exactness for speed.
So what does this all mean? If CKKS uses approximate math, kind of like a busy accountant just rounding numbers to the nearest thousand to save time, the source notes this sloppiness caused a major vulnerability.
It did, the 2020 paper.
Right. In 2020, researchers Li and Micciancio published a passive attack showing that if the results of these approximate decryptions are shared, the secret key itself could actually be recovered. I mean, doesn't that defeat the entire purpose of the lockbox? Are we sacrificing our perfect security just to get the speed we need for AI?
Well, this raises an important question about how we evaluate cryptographic models. Let's look objectively at the mechanics of what Li and Micciancio discovered. In exact FHE schemes, when you use your private key to open the box, the noise is removed entirely. The final answer you read is mathematically perfect.
Okay.
But in CKKS, because the math is approximate, a tiny fraction of that noise remains in the final decrypted result.
Like the accountant's rounding error.
Exactly. And what the researchers realized is that this leftover error isn't just random static. That error is mathematically tied to the secret key. It's an algebraic artifact.
Wait, really? So the noise is essentially a fingerprint of the key?
It is. If a user decrypts the result and then shares that slightly noisy data publicly or, say, feeds it back to the server, an adversary can compare the noisy result to the true mathematical answer.
Oh, wow.
Yeah. By isolating the error across multiple queries, the adversary can reverse engineer the secret key. The attacker doesn't even have to break into the system. They just have to observe the shared results.
That sounds completely catastrophic for privacy.
It required a fundamental rethink, certainly, but it doesn't mean the technology is broken. It means new technologies that solve old problems inevitably create new threat vectors. The standard security model cryptographers use, which is known as IND-CPA, assumed that decrypted results would remain completely private.
But people share AI outputs all the time.
Exactly. CKKS challenged that assumption because in modern machine learning, outputs are frequently shared or fed back into public models. The standard simply wasn't built for that use case.
And the tech industry had to scramble to fix it. The source mentions that major tech companies maintaining homomorphic encryption libraries like Heian, Seal, Helib, Palisade, they all had to implement mitigations.
Right, they patched the vulnerabilities through responsible disclosure before the paper even went public.
That's a relief.
It really highlights how rapidly the ecosystem is maturing.
Mhm.
We're no longer relying on isolated academic papers here. There are standard-setting bodies now. The Homomorphic Encryption Standardization Consortium was formed back in 2017 to maintain community security standards across these different schemes.
With companies like IBM, Microsoft, and Intel involved, right?
Yes, and the technology is robust enough now that it's even expanding into decentralized applications. There are blockchain projects like Phoenix leveraging FHE for privacy-preserving financial use cases.
No.
We have massive open-source frameworks pushing this complex math directly into the hands of everyday software developers.
Which brings us right back to you, the listener. Why should you care about the mechanics of lattice-based cryptography or how a server manages floating-point arithmetic? Because you live your life in the cloud.
We all do.
Every time you use a cloud-based AI tool to draft a sensitive email, or use a financial app to track your personal budget, or a digital healthcare platform to message your doctor, your privacy is increasingly going to depend on these invisible, mathematical locked boxes. As computing power scales up, homomorphic encryption ensures your data doesn't have to be exposed just to be useful.
It represents a fundamental decoupling of data utility from data privacy. For the entire history of computing, we've had to choose between keeping our data secret and gaining the benefits of analytics. That compromise is finally disappearing.
But there is one final thought I want to leave you with, building on the warning from the source material we mentioned earlier. Even with perfect homomorphic encryption, side channels can still reveal metadata.
Right, the context.
They can reveal that an encrypted photograph was sent to a lookup service, even if the photograph itself is perfectly secure. So here's something to ponder as we wrap up. If homomorphic encryption eventually makes the actual contents of our data mathematically unbreakable, will the future of cyber espionage and hacking completely abandon trying to read our messages? Will they stop trying to see the diamond and instead focus entirely on the metadata building, complete, intimate profiles of our lives based solely on when, where, and how often we send our locked boxes?
When the content is silent, the context speaks volumes.
The jeweler might be blindfolded, but everyone can still see how often they show up to work. Thank you for joining us on this deep dive into homomorphic encryption. Keep questioning the systems around you and keep exploring the digital world. We'll see you next time.